Hello?
Hello, Dr. Heinrich.
Can you hear me quite well?
Yes, it sounds very good.
Very good. Good.
How are you doing?
Oh, I'm fine. Thanks a lot. Sun is coming out, spring, so that's always the best time when winter is best. And well, I need sunshine. And it's always a pleasure for me to give some kind of support to young students. And
Thanks a lot.
this is what I like to do. We have a lot of very good talents, and so maybe my speech can motivate them also to do a little bit more research.
Yeah, of course. Thanks a lot, Dr. Hamish. I'm very pleased that you accepted the invitation. I think we have 3 minutes before starting.
Yep.
I think you can see colleagues and students who are attending from the lab, right?
Yep.
Excellent.
So let's check if screen is working. Oops. Can you see my screen?
Yes.
Also in presentation mode now?
Yeah, the presentation is showing that.
Okay, but now I cannot see you anymore.
Even
never mind.
Okay, but even no small window showing the video.
Never mind.
That's okay. But if you open, I think Zoom.
I will let it. Now it works.
Yeah, we can see you. We can see the screen. But I think if you would like to see students in the lab, you might think of maybe opening the Zoom application.
And then go to?
Maybe just open it, and normally it should show that rectangle showing the video conference.
Ah, yes. Now I see something. Ah, okay. Yeah. Yeah. Okay, now I see at least you and me. Good. Okay, that's. So what is
this? I think now you can see the lab instead of me, right?
Yes, I see now. I see the lab. I see CSE admin.
Yeah.
Yellow colored wall.
Yeah.
Very good, excellent.
So I think we have 1 minute. So yes, I think we can start now. So I would like to start by saying hello for everyone, AUCians and everyone attending this seminar from outside the AUC. We at the American University in Cairo, Computer Science and Engineering Department, are really delighted to host Dr. Heinrich Gotzig as our first speaker in this semester seminar series. Dr. Gotzig is a Vallejo master expert with more than 25 years of experience at Vallejo besides academia, with several key inventions and contributions in the automotive industry. And I personally count myself lucky to have been a member of Dr. Gotzig's team in the past few years. The talk is about ultrasonic-based AI, discussing the new and promising area in automotive AI, and how biological principle of bats for environmental sensing can be used to improve the ultrasonic sensor technology. Thanks again, and please, Dr. Heinrich.
So thanks a lot, Hesham, for the kind introduction. Yes, and I'm really happy. So it's a really honor for me to be the first in your seminar. And today I will present you really something which is at least new in the automotive industry, but which is used in biology by the bat. So what we tried to do is to use principles from nature, in that case bat, and to apply it for machine learning. So the work which I present you today is part of the Value internal PhD program, and I will come to that later. So maybe if you have question, either ask it now or at the end. It's up to you. So this is my agenda for today. I will speak only a little bit about Value research and innovation activities, because maybe you're interested in that. And then I will move directly to sensor technologies. So not only ultrasonics, what we developed in our company, but all the other technologies. And maybe at the end, you will understand that what I present today is first investigated with ultrasonics, but definitely all the findings could be applied by other kind of physical principles. So I will speak on ultrasonics, but when you look, then radar, pulse radar is similar, even when you take the same frequency of 24 gigahertz, then we have more or less the same wavelengths. And also when you are talking on LiDAR technologies, all the results, all the findings should be similar. We started with ultrasonics because here we have more than 30 years of experience now, and with ultrasonics, all the computation is much less complex than with radar technology and with LiDAR technology. Then I will hand over to ultrasonics. I will explain how we are doing the signal processing today. And I will have only one slide, to explain you really the basics, how does machine learning works. And then we move to all the research topics with deep neural network and also with convolutional neural network. And you will understand for which kind of cases we are using a deep neural network, and what are the benefits or the advantages of a convolutional neural network. And then we can have a question and answer sessions. So some words on Value, where I come from. So our vision is mobility of the future, which contains 4 different sub-working groups. So the first on the left is automated and affordable. So why not only automated? Some of you may know the DARPA Urban Challenge, which was the very first race for autonomous vehicles. It was done more than 10 years ago. And if you look to the sensor technology at that time, so the cars, they were equipped with a lot of LiDARs, and each LiDAR sensor cost was close to 100,000 euros. And this means for some kind of applications, definitely we can save a lot. But for the majority, when you want to buy a car, then it also needs to be affordable, connected and secure. This means the cars, they are connected with the environment. so the V2X, what you have maybe heard. And for some autonomous driving applications, the car needs to get information from the environment. And here, as a typical example, is valet parking, where we have two different types. Perception is done mainly in the car. This is type 1. Perception is mainly done in the environment. This is type 2. And so type 2, you can see announcement from Bosch and Daimler. Safe and intuitive. This means up to level 3 driving, the driver is somehow in the loop. And we need to develop or to understand in which situation the driver is. Also for cooling systems, when you're going to do sports, then you want to have fresh air on your face, but maybe your legs should be warmed. And the last is service and digitalization. So here we have developed applications like Deliver for You. And this means in the future, parcels or food, they will be transported by such kind of small buses. We have a cooperation with Navia, and this is by principle the basis of shuttle buses. All is a level 4. This is some key figures, and so we are really a big company. In total value has more than 100,000 people. We have 16 R&D centers, a lot of patents. Then we are doing a huge investment in R&D, so typically twice the amount of R&Ds than traditional companies located in 18 countries. 31 production sites, and also kind of standardization. Here you see the footprint, and this will be my last slide regarding Valeo, where we are. And you are located here in Cairo, where we have a very big R&D center, mainly on software and system development, and then all around the world. So we are a market leader. Valeo was worldwide the first going into production with parking systems. We have approximately currently more than 1/3 of the worldwide market share. We have been the first with parking. We have been worldwide the first introducing systems, which is called Park for You, where you can put your hands away from the steering. And we have been worldwide the first company where you can go outside of the car, which is remote parking. And so remote parking means you go out and then the car drives autonomously into a parking slot. Then we have activities on active safety and all this driving automation. So moving more to perception. So Valeo is the company worldwide having the broadest perception portfolio, ultrasonics, cameras, radars, lidars. So currently we are the only company in the world who are in series production with lidar, and we have produced approximately a factor of 1,000 more than the competition. So we have produced maybe 200,000 lidars, and all the competition in total 2,000. So we have a lot of experience, long-range cameras, mid-range radar, and also a near-field lidar. So regarding research and innovation, as I said, we boost innovation by Valeo internal PhD program. So what we do, we offer employees the opportunity of an industrial promotion. So what does industrial promotion means? Typically, people, they are working 40 hours per week. And then we have a kind of an agreement that the PhD candidate has to work 30 hours on normal projects the company pays the additional 10 hours per week, and the candidate is doing also additional 20 hours per week. And when looking to the research topic, so typically we are looking for something which is in our roadmap for advanced engineering. And the industrial interest is that we improve our products, and the scientific content is that we understand the why. So typically with scientific work, we are developing mathematical models, and then the mathematical models, they provide us a very deep understanding on the technology, and the industrial just proves that it works. And what I'm presenting today is a result of a PhD of Mohammed El Amir Mohammed, who also comes from Cairo. He was my very first internal PhD student, together with the universities in Ilmenau and in Heilbronn. Now, when looking to the technical challenges regarding automated driving, by principle, there are three challenges. The very first, which is the most important one, is the environmental perception. So this means the localization and mapping. Where am I? Then the next step, which is becoming then a little bit more sophisticated, is scene interpretation and understanding. Who is around me? And then a kind of a prediction. As we have to do movement planning, so we need to understand how does the situation looks like in the near future. The movement planning is how to get from A to B, and the driver state is what's the driver up to. Now, when looking to all the different tasks, environmental perception, as I said, is the most critical one. And a lot what you see at the moment worldwide means environmental perception with a limited kind of ODD. ODD means operational design domain. Operational design domain is the precondition under which the function works. So when you look to companies, new mobility players, then you see their cars driving very often in very clean conditions, when the sun is shining, when the painting of the streets are very good. But this is then the easy task. The more difficult task is, and I will explain that in one of the next pages, when the ODD gets a little bit broader. This means when you can use the function much more often. And here we need better perception technologies, and better perception technology is that one I will present. So I found a recent article. I will not go into the article today, but as you will get all the documents, you can have a look. So the environmental perception sense technology is really the key for autonomous driving. If we understand the environment, if we understand who is doing what, if we have the right redundancy, precision, true positive, false positive values, only then we are able to extend the ODD, to extend the functions, and to make autonomous driving available for a lot of scenarios. So this is one typical example which we are faced. So on the left side, you see an example where the car drives forward or left or to the right. And next to the car, there is a child, for example. Now, we need, depending on the driving level, either a double redundancy or triple redundancy. And what you see here is we have sensor coverages of different types of sensors. This is a near-field LiDAR sensor. Here we have ultrasonics, and then we also have camera systems. Now, as the different sensor technologies have a different detection areas, provide different kind of informations, are also sensitive to different kind of source noises. So only the fusion will provide the necessary requirements. So here you see the detection requirements, complete set of informations necessary for seeing the interpretation, understanding, and prediction, reliable, redundant information, true positive or false positive means, then a confidence level of the information, depending on the type of applications. We request a different mean value standard deviation. So let's explain that. The faster you drive, the more or the higher the requirements regarding mean value and standard deviation, because this limits your reaction time, and so the precision of environmental perception must be enabled. Self-diagnostic, self-calibration possible. And also there will be a new law that before starting autonomous driving, you need to do a kind of predictive performance. This means no degradation while driving from A to B. So now we come to ultrasonics. So this is the basic principle of ultrasonics technology. So the ultrasonics they are used in automotive for perception, in ADAS system. ADAS is autonomous driving systems. And the basic operation is that the sensor, which is mounted here, fires an ultrasonic pulse, a wave, and then via the piezoelectric effect, the sensor detects the reflected energy, and then this is the basis for all the distance calculations. So when looking on functionalities, we have SAE L0 and L4 parking. So L0 is a pure park assist, and L4 is the valid parking. And valid parking means that you have a drop-off zone at the entrance of a parking garage, and then the car gives control to the system, and then the car drives autonomously to a parking place, and you can call the car back with your smartphone, and then you can pick up in a pickup zone, blind spot detection, and much more. This is the basic principles of machine learning. So here in that case, you have a deep neural network. So deep because you have one input layer and some output layer. In that case, it's machine learning for figures. So you have the pixels. The pixels are either green or white. And then you have to do a kind of calculation similar to how the human brain is working with inputs, with a kind of threshold functions, and then a kind of an output. And now then depending on how the neuron works, you will have a dedicated output. And then at the end of the day, it's only a cost minimization problems. And this is really the pure basics of how machine learning works. Definitely in reality, it's much more complex. And for image processing, you have maybe hundreds or even thousands of hidden layers, which makes the need of GPUs. So when we started the PhD, what was the basic question? So the ultrasonic sensor transmits a pulse, which is called the TX, and in parallel it moves into an RX mode, And then we defined three different problems. The first problem is whether the echo comes from a real obstacle or from noise. So we have two classes. Then the next task, whether the echo is relevant or non-relevant for autonomous driving. And non-relevant means that they are reflections coming from the ground. Once again, two classes. And the third is the type of the obstacle. And in our case, we tried to achieve that we have a kind of a classification height of obstacles, because we want to understand whether the obstacle is lower than 20 centimeters, between 20 and 40, 40 and 60, and higher than 60 centimeters. So for that, we built up a big test equipment, recording all the data. And so we started with a very first concept, 4 layers, then 700 input nodes, and 2 hidden layers, each 500 nodes. And we started with training. So what you see here is a typical example. Here, this is an ultrasonic pulse when we are doing measurements on asphalt. And here is the raw signal of an ultrasonic sensor when we are doing measurements with gravel. So the motivation is also, in addition, we have here external noise. External noise could be, for example, clinking keys, truck brakes when it heavily rains, and so on and so on. And we need to understand whether the information is reliable or not reliable. So the task is detect relevant obstacles and filter out all of the non-relevant obstacles. So this is the existing solution. So once again, a typical example of an ultrasonic sensor. This is the time-dependent information. So here the amplitude and here the time. And typically what we are doing is a kind of a pre-processing. So we apply a kind of a filter, a band pass filter. And then we have a kind of a noise reduction. And then traditionally, and this is how almost all the OEMs are doing it, we compare the height of the echo with a so-called threshold value. So the green is the amplitude coming from the sensor, and the red is the threshold value. And if the energy or the voltage from the sensor is above, then it's digital 0. And when the energy is below, then it's digital 1. So this is the kind of information which is used at the moment by all the ultrasonic system suppliers in the world. Now, this is the approach. And when you look to this picture, then you see that we transmit a pulse. Here we have a kind of an obstacle. And then the shape of the pulse, so this is the TX and this is the RX, strongly depends on the shape of the obstacle. So what we did here, once again, the RX is a function of the TX, so what you transmit, and also on the shape of the obstacle. Here's the information from the ultrasonic sensor. Here is once again the raw signal. And then we are doing some kind of AD conversion with the signal and feed our map, and then doing a kind of classification. So in that case, it was a supervised learning, because we know the result, and then we are using this for training the data. So we have data or a training set. So we did a lot of traces from ultrasonic sensor sampled at minimum doubled Nyquist rate to avoid any kind of ghost signals. We have done measurements with different obstacles at the different angles, distances, and so on and so on. And one of the very big targets is what can we achieve using a very small microcontroller? So when you remember in the beginning, I said automated and affordable. And really, when looking on machine learning in automotive is mainly used for image classification, so computer vision. So really the idea was what is possible with a very small 16-bit microcontroller with very, very low processing power. So this is what we did. As I said, we have an input layer of 700 neurons. Then we've used 2 hidden layers, each 500 neurons, and 2 neurons as the output. So with the classification, relevant, non-relevant, real, not real, and of course for the height, where we have 4 classes, then we use 4 classes. So this is the very first results, and I can tell you we could do all the investigations with a very small microcontroller, 16-bit microcontroller, only with 30 kilobyte of RAM. So this was enough, and this is the result. So typically, when you want to classify the performance of a classification task, then you use the so-called F1 score. And F1 means when all the classifications, when true positive is at 100%, then you have an F1 score of 1 that you see. And when there is no classification possible, this means you cannot predict whether your forecast is correct or not correct. This results in an F1 score of 0.33. This is the definition, F1 score, so true positive divided by true positive, half of false positive and false negative. Here you see the results of 4 different types. So starting from the left to the right. The left is what we have done traditionally. So that's what I explained to you with threshold values. And the next one is a kind of a correlation. This means we multiply the received signal, in best case with a transmitted signal. And this gives the very first significant improvement. But finally, when you look to the blue and the orange one, even very good results are possible at a negative signal-to-noise ratio. This means when you operate in a very noisy environment, this kind of technology provides very good results. And so these are the samples from asphalt. These are the samples from gravel. And what is obviously is that machine learning with ultrasonics provides a very big potential, and only with very, very low requirements regarding the hardware. So these are the results. So the neural network was trained both on asphalt and the gravel. We have optimized the threshold values, and only this is with the threshold values. They give suboptimal results. And with machine learning, it's possible to measure even in a very, very noisy environment. And you remember in the beginning when I explained the ODD becomes key. So today, the majority of all the systems, they operate in a very limited ODD. But once, when we are able to measure even in very noisy environment, then we can extend the ODD. And this is what the market expects, that the system is able to drive autonomously in almost every driving conditions, and that you don't have to wait. So the next, what we have started is noise suppression. So noise suppression, here we have rented ideas from the music industry. So the music industry separates vocals from music, and we tried to apply that. So the target was to remove noise artifacts from the ultrasonic signal. So this is typical signal with some kind of noise artifacts, and also to introduce a minimum distortion to the signal. So why minimum distortion to the signal? So typically when you apply some kind of filtering technologies, this also means that you change the shape of the signal. Now, I explained to you that the shape of the signal contains directly information on the type of obstacle. So when we are doing a kind of a noise suppression and want to apply machine learning, then we have to ensure that we do not have a distortion of the signal. So the existing results are discrete wavelet transforms. So discrete with discrete wavelet transform, you do a first transformation from time into frequency domain. Then you apply a kind of a filter technology, adopted filter technology. And then you're doing the transformation back to the time domain. So multi-layer filtering, we had real-time constraints, but I will show you that with this kind of investigations, we even arrive at real time. So what did we do to achieve the noise suppression? So for this, we applied a convolutional neural network. This is a biological inspired concept of machine learning, in particular to work with pictures and audio data. So here, the convolutional neural network is very good when you want to detect classes. So you remember in the first task, we only want to distinguish between two classes. But now the system learns the class, and the system learns which does not belong to the real obstacle. The benchmark, what we have done was against wavelet transform. And so we made a comparison between the wavelet transforms and the CNN approach. Here you see the examples. The pure signal, this is the pure signal. This is the signal with noise, and this is noise suppressed signal. So here on the upper, you see this one is with noise, and then you see the difference between the solution with the discrete wavelet transformation and with the CNN approach. Here you see that the shape remains more or less the same, which is the CNN denoising. And here you see that something disappears. And so even if discrete wavelet transformation provides good results at a very good signal to noise ratio, it fails when the signal to noise ratio is more or less equal. Now I will skip. Can you see the video?
Yes, Dr. Heinrich.
Okay, so what you see here is in real time the input and the output. And so what you see is that we achieved that in real time noise suppression is possible. So once again, this is a signal with noise, and so this is the same time scale, that with this very small convolutional neural network, we were able to suppress the noise in real time, which is a requirement for environmental perception. So we need a kind of timestamp. Here the performance, and when you approach 0, 0 means that the noise level is more or less exactly the same as the energy level of the signal. Then discrete wavelet transforms, they fail. But with our convolutional neural network approach, we were able to measure even at a negative signal to noise ratios. So now I come to the conclusion, and then we can have question and answer sessions. So regarding classification, so really it outperforms existing approaches. And the existing approaches is that what all the sensor suppliers are using, the threshold comparison in classifying echo and noise. And so the machine learning approach is highly independent from pre-processing and the terrain. I showed you examples from gravel and from asphalt, also from keys. So it's really a good approach to clean the signal. And then I showed you what we have done in this research work regarding suppression. So traditionally, state of the art is a discrete wavelet transformation. And the discrete wavelet transformation transforms the signal from time into frequency domain, then applying a certain kind of filter technology, and then again moving to the time domain. It works when the signal to noise ratio is good. But when you enter into situations when you have a very, very noisy environment, then the traditional technologies fail. Now with the approach of a convolutional neural network, even in real time, it's possible to clean the signal, and the cleaning of the signal is possible without modifying the shape of the obstacles. And then this is the basis to do further investigations to even extend the ODD much further. And this also may be the possibility to meet SOTIF requirements, so the safety of the intended function. So the system who is doing the perception, environmental perception, needs to understand the quality of the signal. And by using our approaches, we can do a kind of a cleaning effect. So we can remove artifacts. And then for the next processing steps, we can use a clean signal. Now, what you have seen today is the first approach with pulse sensing technologies. Machine learning is typically used with computer vision. But the same principles apply also for radar technologies. Okay, radar is maybe a little bit more difficult, as the reflected energy strongly also depends on material constants, so dielectric parameters. and it also can be used for LiDARs. So for example, when you have a fog, then the light is scattered, and this means the signal broadens, and by analyzing this broadening effect of a LiDAR sensor, you can get an information how foggy is it, how big maybe a drop size, and so on and so on. So there's a huge potential for further investigations, but at least based on this research work, we could demonstrate that machine learning is a good alternative. We don't need that high computing power, and the results are really very promising. So now I'm open for hopefully a lot of questions. So we agreed that I speak 40 minutes, so I take exactly the time.
Yeah. Thank you so much for the excellent presentation and the very interesting and promising work, Dr. Heinrich. And of course, for all of your keen efforts and wonderful contributions with the new internal PhD program. I believe it's an excellent opportunity for engineers who target to develop a career that bridges both academia and industry in computer science, which is something that is very important to this seminar audience. So please allow me to allow Nada Morsi from CSE team to lead the Q&A session. Thanks again, Dr. Heinrich.
Thank you.
Hi. Thank you again for coming here and giving us this amazing lecture. I actually had a couple of questions myself. So for someone to work in the field that you just described, and with all of that machine learning and mathematical background, which major or what is the best thing that they should study to be able to work in that field?
So first of all, you need to understand the basic machine learning, the different technologies, and also you need to get a kind of an understanding what kind of informations can be extracted out of which kind of sensor technology. So I give you one additional example. I have running at the moment another PhD, also using machine learning, but in that case we are using spiking neural networks with neuromorphic chips for 3D point cloud classification of LiDAR sensors. So my recommendation is first learn the basic principles of machine learning, because the key challenge is the design of the net and which kind of net you use. So today I've talked on deep neural network, convolutional neural network, and also where you can apply this kind of new technology. But mathematical background and system understanding is very important.
Oh, okay. So like and there is a hardware aspect of that as well. So to what extent should an engineer or like the person who's designing these devices should know or be aware of what they're dealing with? Any is it more of software or hardware? Oh, go ahead. Sorry.
So in general, we don't distinguish between hardware and software. So typically, people are using a kind of an FPGA with which they can simulate different kind of hardwares. That's what we are now doing at the moment with this spiking neural network approach. And then the target is, from a software point of view, how we can optimize that. I will give another example, what we have done in this work. So we started with recording with 1 megahertz. So the Nyquist, the operational frequency is 51 kilohertz. So when looking to the Nyquist theorem, you should sample with minimum, let's say 150 kilohertz. But we start with 1 megahertz. And we also did the sampling starting with 14-bit then 12-bit, 10-bit, 8-bit, and 6-bit. And we even found out that even with 6-bit, we can extract some kind of information. So to answer your question, start with FPGA and then try to optimize. You need to understand what kind of informations you need to extract. And for this application today, it was only of interest. Noise, no noise, relevant, non-relevant. And then depending what your perception needs, you can select different things. Also, the one slide, which I showed you the example of the pedestrian laying on the ground. So definitely everything will not be able to be solved with one single sensor technology. So it's the combination between different physical principles, and then it's up to you to define which kind of information needs to provide it by which kind of sensor technology, and then this also has a direct impact on the hardware you need, on the kind of informations you have to process. So it's an approximative way.
Okay, there's a couple of questions from the audience. I think it's from Abdel. Would you like to ask the question, or would you like me to ask it for you? So I'm gonna go ahead and ask it. So the first one is, did you find that training data set require many measurements with varying temperature and humidity? That's the first one.
Yeah.
Okay. And are temperature and humidity among inputs to the NN?
That's correct. So what we are it's definitely a combination between real data and synthetic data. So our approach is that we record data at different temperatures, and then having also developing in parallel, which is a different kind of work based on that what we know synthetic data. So definitely it will be impossible to record all the different scenarios. We have done some kind of estimation, and I have to guess now, maybe less than 10% of all the data which we can record are really real data, and the other one are synthetic data. So it's necessary to develop sensor models, and then use what we call the digital twin, describe the scenarios in a digital world based on models which are proved by real data. So that's the approach. Sensor, so have a sensor model, prove that the sensor model works based on real data, and then optimize your model. And we have a plan for another research project. So first, validate that the simulation or the synthetic data are correct, and then finally do a kind of a certification that you are able to use this data, and that's the approach. I hope I could answer your question, but you need sensor model. You need to understand how the varies as a function, for example, as a function of temperature.
Okay. So another question from Ahmed Azab: why CNNs were used for audio instead of RNNs, and how CNNs extract features from audio?
Good question. Because my student Shauki, he has studied the literature, and in the literature he found that the CNNs are already used in the music industry for the separation between vocals and music. So he used investigations, already existing investigations, but transformed it to a new kind of applications. So we never have studied if RNNs or CNNs is better. We only used what already exists and transformed it to this new application, and it worked. So it's only one word, but definitely there is a lot more.
Okay, I think that's all. I would like to thank you all again, Dr. Hesham and Dr. Gotzig, for coming here and helping us with this, giving this speech, this talk, I mean. Yeah, thank you. Does anyone have any other questions? Oh wait, I think I missed someone's second question. 1 second, I'm sorry. Oh, it is. How about the second CNN, which probably requires more powerful specs to deliver a result in real time?
So yes, it requires definitely a little bit more computing power, but a maximum, as I said, of power of 5. Even with a small microcontroller, 16 bit and 30 or 40 kilobyte of RAM, it works. So we don't need a huge GPU from NVIDIA or NXP to do all the processing, because we have limited amount of data, and so it works quite well, and we can do it in real time, which is not possible with GPUs.
Okay, so does anyone have any other questions before I end today's session? Okay. So again, thank you all for coming here and for giving us this amazing talk. And I hope you have a great week.
Thank you, and good luck with all your research activities.
Thank you.
Thank you. Bye bye.
Thank you so much. Thank you so much, Dr. Heinrich.
Bye.
Thank you, everyone.